Yeah, so I will start from a short presentation about what Kangaroo is about. This will be, I don't know, maybe third or fourth time that I'm talking about this, but it's good because you will remember that better. You know that term already. It's about simulating something inside computer. Doesn't really matter. This is the plugin that we will learn today, Kangaroo Physics. It's used for simulations, for real-time simulations of physics in Grasshopper. And those simulations are based on a particles spring system. And now I will explain to you how it works in detail, and then we will have a simple hands-on. In general, Kangaroo is a component that has a loop inside it. So it's like anemone, but packed inside a component. It works on its own, and it has a few options about how it displays the process of the simulation. Basically, it consists of goals. So goals are like forces in Kangaroo, and you have the engine that runs the simulation based on the goals that you set. And there are some also utility tools, especially for processing meshes. And because Kangaroo is built in Rhino since version 6, then well, it's pretty useful, especially because of those utility methods, I would say. There are a few mesh processing components that would be missing in my opinion if they were not in Grasshopper at all. Okay, so what is a particle spring system? Basically, everything in Kangaroo is either a node, so a point with some properties, or a line, so something that connects 2 points. We also call them a particle for nodes. So this is an element that, and also only the nodes can be affected by forces. So just the particles, only they can be affected by forces. And the springs are something that transmits the force. So a spring can have its own properties, and basically it drags or repels two particles from each other. That's what I would say. So we have just the nodes and just the struts. That's all we have in Kangaroo. And everything bases on the second rule of Newton dynamics and Hooke's law, which means that the force is proportional to, for instance, how much you extend the spring. That's the Hooke's law. And the second rule of Newton dynamics is that the velocity is proportional to the force applied to a particle. So that's something that you already understand, which is good. That there is a difference between continuous and discrete objects. Basically, the native kind of geometry for Rhino is NURBS geometry, as you know. So before we process anything, let's say native in Rhino, we need to convert it to a discrete object. So we would convert a NURBS curve to a polyline. That's something that probably I also told you about some time ago. That you should remember this term. Actually, what is a discrete element, and what does it mean to discretize objects? Basically, it is that you change the continuous into something segmented. So instead of having a continuous curve, you have a segmented polyline. Or instead of a continuous NURBS surface, you will have a segmented mesh. So that's what discretizing is. And you can think of discretizing as well if you, for instance, you draw a building. You just think of walls as continuous volumes. But in fact, they need to be discretized before they are built. They are discretized into bricks, into prefab elements, into whatever. So you always discretize, in fact, because we need to have a chunk of material or data. Anyway, that's the same, but for surfaces. So you already know what meshes are, thanks to our first exercise, and what is the difference between a NURBS surface and a mesh. Basically, it's about how they are modeled, how they are described, and of course, how precise they are. So, and the same applies to meshes. So whenever you want to model something like a surface in Kangaroo, you need to discretize it, and you also, in a mesh, have something like nodes and struts. you have vertices and edges in mesh, as you remember. Every mesh constitutes of vertices and faces. And if you process the list of vertices and faces, you will also get edges, and edges are what connects the vertices. And if you convert a mesh to a Kangaroo object, you will get something like that, a net, basically. So once again, to summarize, Kangaroo is a solver for dynamic systems. It's not, I wouldn't say that it is anyhow realistic, because you are not using real units. You are not, you don't input anything like tensile strength or anything else. I mean, you don't input any material properties. All you care about is the dynamics of particles and springs and the equilibrium of the system. And you have two types of elements, so you have nodes and struts. Struts are for strength, so for forces, basically, and nodes are what is affected by those strengths. And that's all. That's enough of theory. Now let's open Grasshopper and let's see how it works in practice. All right, I told you that you have three kinds of components in Kangaroo. First of all, let's find Kangaroo. We will use Kangaroo 2. I don't know if Kangaroo Kangaroo has two versions, Kangaroo 1, or more specifically 0.99, which is good sometimes. I don't know, I can't recall for now when it's good, but it has the older version and the newer version. I suppose that only Kangaroo 2 is installed on your computers. That's fine, because we will use Kangaroo 2 for today. And as I said, there are three kinds of components. You have goals, you have the engine, and you have the meshes. So for now, let's focus on the solver itself, or the main group. And you can just pick all of those components and put them on canvas. Okay. So I will tell you one by one what they do, very briefly. Some of them, I don't know, honestly. Okay, very quickly. So show is a special component that allows you to selectively pick geometry for the solver. Doesn't matter for now. Bouncy solver is something that we will use. It's the default Kangaroo solver. It's called bouncy because it allows us to see what is happening in real time. Then we have soft and hard solver. Honestly, I have never used it, so I won't explain it to you right now. Probably would need to test it. Then we have zombie solver, which is the same as bouncy, but zombie means that you will get just the final effect. So it's similar to anemone set to output after the last iteration. Then we have just the solver, and I'm not sure, but solver and bouncy solver, they work quite similar, but they are different because of those two settings, damping and iterations. And yeah, we would need to, yes, so this is with momentum. So it means that there is some, how do you say that? Forgot the word. Even in Polish. Bezwładność of the system. Do you know the word for that? Never mind. And then there is grab, which allows us to pick the form with a cursor, and step solver, which will just do inertia. Yes. And so step solver allows for simulating something frame by frame. From what I know, you can just select the frame of the simulation. So for the first example, we will use just bouncy solver. And you need the solver every time because, as I said, it's the main engine. And what you will need to put on canvas every time as well is a Boolean toggle for for turning the simulation on and off. You might use a button for resetting the simulation, and also something to control the number of iterations between frames of the simulation. So I would input a slider here from 1 to 10, just to show you the difference between different settings. I think that by default iterations is set to 10. Of course, this is not, it has a default value, so you don't need to put that slider, but it's good to have control over how it looks. Okay, and now the simplest simulation that we can think of. Our simulation will just take a particle, and we will apply a gravity force to it, and this particle will just fall. So that's what we will do. So first we need to model the particle, and that's as simple as just putting a point somewhere in space. So set one point, put it in Rhino, and maybe just drag it up so that it's above the construction plane. Okay, and now you don't explicitly input geometry to the solver, but you have to create the forces. So I told you about those goals, and those goals are forces, as I explained, and they are categorized by geometry that they can affect, or something that is relevant to those goals. So you have goals for meshes, so these goals will affect whole meshes. You have goals for points. You have goals for preserving geometry on other geometry. You have goals for lines, etc. So in our case, goals for points are relevant, and we need to apply a load to that particle. So please select the load component. And we need to simulate gravity with this. So we will use point as a point. So that's the particle that will be dragged. And we need a force vector, which will be inverted z-axis. Okay, and in fact that's all. So you can already set up the solver. So all you need to do is to put the goal. This is a special object, as you can see. If you input it to the panel, you will just read the description. It's the type of the object. So the type is goals unary, so unary goal, unary force, and just input that to goal objects, and then run the solver and see what happens. So you need to turn it on, of course, and you can reset it. You will notice the difference between a number of iterations. So I told you to set it to 1 initially, and this is because you will see more frames. Because if you set it for 10, for instance, then you will see only every 10th iteration of the system. So 1 is the smallest value. I suppose that you could, if you want to change something in Kangaroo, most of the times you need to experiment with the settings. So if you would like it to go slower, then most probably you can just reduce the strength, for instance. So reduce the length of the force vector. Then the particle will fall slower.
Why in here the shell component is not?
Okay, so that's the basic simulation. Now let's add something more, and that's also something that you should remember. As long as you will use Kangaroo, we will add additional goal object, which is the floor. So we will floor basically is an object, very generic object, which creates a floor on the construction plane, on the XY plane, and it's how do you say that? Forbids any particle to go through the floor, basically. So it will stop our particle. And what people do very often is they simply put goals together in goal objects input like that. So they just drag the wire and press Shift key and do it like that. And you should never do it like that, because you will lose the order of goals on the list. Or if you won't lose them, because it is dependent on the order in which you put the wires in the inputs, it will be invisible to you later. So you won't know what is happening. So every time you combine data, you should use merge, so you control the order of elements on the list. And every time you combine goal objects for Kangaroo, you should use merge as well. In Kangaroo 1, so the previous version, there was a common error that goal objects were input as a list. And sometimes, as you know, when you merge data streams, you get a data tree, even if you didn't mean to, because of different paths of lists. And in the previous version, there was a common mistake where a few simulations were run at the same time with a few separate sets of goals, and you usually needed to merge the goals and flatten them, but it's not the case anymore. It's the goals are flattened anyway inside the solver. Okay, so if you have the floor already, then you can reset the simulation and see what happens. So basically, the particles should bounce off the floor, just like that. So that's the most basic simulation. Let's see what would be the difference between the bouncy solver and the regular solver. So we will also need the reset and toggle. So just use the solver, regular solver, and yeah, it doesn't do anything. So yeah, this solver just outputs the final result immediately in this case. So that's the difference. So we will use bouncy solver for now, just to see better what is happening in the file. Now there are a few outputs of the bouncy solver that you can I will just tell you about the component itself. So you have the iterations, so how many iterations of the simulation have passed. You can see the parallel with anemone, right? Because this is the same. Something is executed in a loop. Then you have V. V is a list of vertices of your model. So these are all the vertices, all the nodes. And the last is the goal function outputs. So these are the goals. And sometimes they contain geometry, sometimes they don't. And in our case, we have two nulls because a unary force and the floor, they cannot be represented as geometry. So I will tell you later how to put any geometry in the goal function output. Okay, do you have any questions for now? No questions. Okay, so let's do another example. So in the other example, we will create a system where we have two nodes connected with each other. So something like that. Basically a hinge. And this one will be anchored in space, and the other one will be dragged down by gravity. So this is the simulation that we will do. So we need to have two nodes, basically. So let's keep it very explicit. So 2 points, 2-point components, and just set 2 points in Rhino somewhere. Maybe drag them up. And now one of these points will be just dragged down by gravity. So we will repeat what we did before. So let's say that this second point will be the one that is dragged. So once again, we need unary force goal. Actually, not this one. This is for Rhino for first Kangaroo. Probably you won't have this problem because you have just the second version. Okay. Yeah. Thanks. So you have the points and again the force vector. Of course, this could be, it doesn't have to be gravity. It can be any force in any direction you want, but we just want it to look a bit realistic. So we have the load, the unary force, and then, so this is the same as before, and then we have the anchor. So this point will be the anchor. We want it to stay in place where it was. And the anchor goals are also in goals for points. So you have anchor, and there was a plastic anchor. That's something that I used quite often. It's an anchor, but an anchor that can move, and this one will allow you to preserve the position and keep it only around specific axis. So for now, it doesn't matter. Let's just use the typical anchor, and let's combine those goals together. So again, merge. And the solver, of course. Okay, and let's run this simulation and see what happens. So nothing visible happens. I will reduce the number of iterations. 1. Okay, so as expected, or maybe not really expected. So one point just falls down and the other stays in place. So what's the problem here? Exactly. So there is no force between those two particles. There is nothing that keeps them together, and now we need to include that force as well in our system. So we need to create the connection or the strut between the 2 points. So just create a line. So we created a connection between those 2 points, and we added the length, the goal that preserves distance between 2 points, and we put it as another goal in here. So right now, in every iteration of the loop, Kangaroo first of all applies a constant force to one of the particles. Another is constantly held in place, and also every time the distance between those 2 points is tested, and if it is different than the length specified here, it will be countered with another force. So it seems pretty. It's quite simple, but works. So once again, we have the anchor. So in every iteration, it is if if it is moved anyhow, then it will be dragged back to the to its origin. Then we have another particle which is constantly dragged by the unary force, and we also have this spring which tries to preserve its length. So whenever it elongates, it tries to get back to its initial length. So this is the dynamic system that we just implemented. Yes, okay. So we can change the rest length. It's here. By the way, it's not a factor. So if you put half here, then it will be half of a unit, not half of the length. Okay. So in my case, it would be okay. So it would be around 17. Let's simulate what you have on your computer. And yes, you're right that it instantly, very fast, tries to get to these lengths. So you could reduce the strength of this, and then it will be just it will be less strong. Okay, so this force will be multiplied by a scalar, and every time the reaction to any modifications of the system will be smaller a little bit. And as you can see, if I decrease it even more, then it will be slack, like a rubber. So strength is, and if you would like to have something extremely stiff, like a strut, like a metal piece or something, then you would need to increase the strength. And here, this is quite interesting why it's going so slow. But the reason for that is that right now in every iteration the movement is very tiny, because the strength of this load is every time countered by the strength of the strut, which means that it tries to move like that, and then it is countered by a very heavy force in that direction, and the resulting vector is very tiny. Let's say the vector that goes down is very tiny, and this is why it slows down. Anyway, you have there is no recipe for setting those strengths. In general, you have to keep them proportional between different goals. So you need to adjust them to your for your project. There is one more thing that I didn't tell you about yet. It's this label beneath the solver, and sometimes it changes to converged. Basically, it's about the tolerance. So if any movement in consecutive frames is smaller than the tolerance, then the solver will converge, which means that it feels like it achieved an equilibrium, so all the forces are balanced, and then it can stop, so there is no change in the system anymore. So when it's converged, then it just finished the simulation. All right, and let's make the last example before the break. So the last example will be a chain structure, a catenary structure. So we will have two anchors. And the chain. And this chain will be also dragged down by gravity. So that's the system that we will make. So we'll have more nodes this time, and two anchors, and we will learn how to input many nodes at a time. So first of all, we will need to start with the most basic setup. So we need those two anchors. Maybe let's also create them explicitly. So this will be the two anchor points of this catenary structure that cannot move. They don't have to be on the same level, of course. And we will create a line and shatter it into smaller pieces. So, line. Then, how do you shatter a line into pieces? You need to divide it first into segments, not this component, divide curve. You pick a number of divisions, so I will choose 50 maybe. And what we get from divide curve is a list of points, a list of tangents, and a list of parameters, and we will use the list of parameters to shatter the curve. All right, and what we get from this component, the segments, they will be our springs of the system. So we have the nodes, you can see them, and we also have the springs. And this all will work, these all elements will work individually. So let's just label them for so that it is more readable. So we have this, and we have the points as well. And I will call those lines springs or struts, up to you how you call them, or edges. And here we have nodes. So we have the nodes and we have the springs. And now we need to apply, first of all, we need to apply gravity force to the nodes. So load. You input we do it exactly the same as before. So just the points. Maybe let's keep it the same. So inverted Z. So this will be our gravity. And maybe let's do it one by one to understand what all of these goals do. So bouncy solver, let's set up the solver with just this one set of goals. So yeah, goal object, button for the resets, and toggle to switch it on and off, not this one. And one iteration per frame. Mm-hmm. And yeah, if you run this simulation, then as expected, all those nodes will just fall down because nothing holds them together. So we need some more goals here. So first of all, let's connect them together into a chain. So what we need to do is we need to convert all those lines into the length line goal. So that will be our another list of goals, length line, that's this one. And it's up to you what length you will use. I prefer to stay with the base length, so just like that. Of course, you need the merge components again, so you don't, so you keep a proper order. You can flatten this here, but it doesn't really matter. And this will work, but of course they will keep together more. They will just fall down like a chain. So in order to add the last required goal, you just need to select proper items from the nodes list. And I don't know if you remember that you can just use the list item with the default index set to 0 and zoom in, add -1, and you will get the first and the last object. from this. And this is basically how I would create those anchors. So then anchor, and this should be another gold here. And we have a nice chain. I think that it's a bit too slack, so probably the strength of this length should be, length goal should be a little higher, maybe 10 times. And this can be also a larger number. Okay, that was all, the first part of the tutorial. That's it.